what is fairness in software first? A software is unfair when it discriminates people based on their societal attributes, like race, sex, or age, or any other religious faith, etc. We call these attributes protected. So when some privileged individuals or a group gets systematic advantage from the decision of the software, it is not fair. For example, when a bank approves loan based on their records of the client, it should not discriminate based on the race of the individuals. Yeah, that's the ideal and the initial idea of fairness. And at present, a lot of data-driven software are being developed, and many of these software affect human lives directly. We use data-driven software in like credit approval or employment decisions or admission decisions, even in jurisdiction of courts. And in our university at Iowa State, we have the Transdisciplinary Tripods Institute, D4, the main goal is to ensure the dependability of data-driven software. And as part of that overall goal, I am investigating the fairness property of this software. Yeah, here is some examples from recent past, which shows violation of fairness in real world. So in this one, you can see Google Translator has found to show bias while translating from English to Turkish and again back from Turkish to English. So Turkish is a language where there is no gender pronouns, but you can see when translating, he has been she has been assigned to nurse and he has been assigned to doctor, which was the opposite in the original sentences. Here is another one. In 2015, Amazon used a secret AI tool to filter their job applicants. The tool was reported to discriminate people like men and women. Basically, they were penalizing the resumes of women more than men. So, recently we experienced many of such fairness violations. Minority people received biased decisions, facial recognition, and automated pricing favored some people than others. And even in crime prediction of courts, the predictions have been shown to be violated the fairness requirements. All right, so firstly, we have this continuous effort to eliminate social discrimination, and people should not get advantage or disadvantage because of the prediction. And oftentimes our software, what it does is it algorithmically or systematically encodes bias. And bias could be from different, bias has been studied in like data science for a long time, that like a data bias or data collection bias or the sampling biases. But here we are mostly focusing on the algorithmic bias, which is the fairness of the machine learning software. So when we are learning from the data, the algorithm is supposed to learn in a fair manner, and the predictions should be fair in any way. I mean, irrespective of if the data is biased or if it is if the other factors are also biased. So mostly in my research, I have focused on the algorithmic fairness. In recent few years, a number of studies has been conducted in this area. Mainly 3 different communities looked at this problem very closely. The first is the machine learning community. They proposed the theory and metrics to measure algorithmic fairness. Also, a few bias mitigation algorithms have been developed. And secondly, based on surveys and interviews, human-computer interaction community studied the ethical aspects and how fairness is perceived by the community. And third, the software engineering community has mainly focused on fairness testing, especially like on automated test case generation for fairness. However, we are not aware how much fairness issues exist in ML models in practice, and what are the software constructs that affect fairness, or how can we like ensure formal guarantee of fairness and so on. So I mostly focused on those questions. All right, so today I'll mainly discuss about my FSC 20 work, which was an empirical study to understand fairness in the real world, and then in another work that was published in FSC 2021, which was fair pre-processing. In that one, I was mainly focusing on understanding the compositional fairness in different stages of pipeline. So not looking at the fairness as a whole holistic property, but looking at how we can localize or how we can say that this component is unfair. I will also talk a little bit about the work on understanding the software architecture of data science pipelines. And finally, I'll talk about the verification of fairness that I'm currently working on. So let's begin with the empirical study that focused on the real world situation of fairness. Software requirements have been evolving over the times with the functionality and performance, reliability. We have to ensure the fairness of the decision as well. So in software engineering research, we study defects or bugs which violate these requirements. We localize and test and fix these problems. But so we envision fairness as a similar issue in software engineering, which also needs to be addressed with respect to all of this. Fairness testing has been studied in last couple of years extensively by the community, but we need further tools, methods, or languages to focus on these activities with respect to fairness. Here is an overview of this work. We wanted to study how fair the models are that are wrote by machine learning practitioners. So first we created a benchmark of machine learning models, and then we answered these 3 research questions. The first is, what is the fairness measure? So since there are a lot of definitions of fairness in the literature, we tried to use different metrics to understand and their trade-offs, as well as the trade-off with the accuracy. Like this is a common understanding that when the accuracy goes up, the fairness goes low. So we first started the measures, and then we looked at the root causes, and along with that we tried to apply mitigation techniques available. So we took some off-the-shelf mitigation algorithms and applied on each of those models. Finally, we looked at the impacts of those mitigation techniques. This is how we created the benchmark. For creating the benchmark, we have collected models from Kaggle. So Kaggle is one of the most popular data science platforms where we can host a competition or take part. So there are competitions and open data sets in Kaggle. We have gone through the Kaggle tasks and identified 5 dataset tasks which are appropriate for the study. And then we have gone through the process of filtering and manual slicing. So basically at the end, we have got these 5 different data sets, and for each data sets, we took the mostly rated or accurate models, like 8 models from each category. So we got a benchmark of 40 models. And yeah, as I was saying, many fairness definitions have been proposed in the literature. So there are these 2 main categories of definitions. One is group fairness and other is individual fairness. So the group fairness, as the name suggests, measures the fairness among different protected groups. For example, if sex is the protected attribute, men and women are 2 groups, and we evaluate that whether the prediction is similar for men and women. So if the application is approving loans, so we actually measure if similar ratio of loans are approved for men and women. Individual fairness, on the other hand, does not consider the groups. It looks at individuals separately. So 2 valid inputs should receive similar outcome, even though the input differs in protected attribute. That is individual fairness. So basically, if 2 persons are very similar, but they are different in their protected attribute, say race, but still they should receive similar outcome from the prediction software. So yeah, I'll talk about a few of the definitions in detail. So suppose D is our data set, and X is the training data, Y is the training labels, and A is the protected attribute. So we divide the labels in two different groups. One is basically if the decision is favorable, or otherwise it's not favorable. For example, if crime prediction, if it is predicted positively, that is basically the the software is trying to say that this person will do some future crime, so that is unfavorable. In loan prediction, if it approves the loan, that is favorable. And the other thing is the protected attribute. If the protected attribute, there could be many races or multiple genders, but so we divided it into two, like privileged or unprivileged. So it is divided based on the historical data, like which race or which gender has been historically been privileged. And then we calculate the probability that an unprivileged group gets favorable decision. So the unprivileged group gets favorable decision, and this probability says that the privileged group gets favorable decision, and the metric, which is called disparate impact, it actually calculates the ratio between these two. And in statistical parity, so this doesn't calculate the ratio, but it takes the difference between these two. So this is how a group fairness is measured. And several other, these are these two, DI and SPD, but there are some other definitions which follow the similar concept. And for example, in EOD, instead of predicting the probability, it calculates the true positive rate, which is also the probability of the qualified individuals. So true positive rate for both unprivileged and privileged, then it takes the difference. And the other metrics follows the same concept. Yeah, I'll talk about the individual fairness in detail. So suppose X and X dash, so these are two different individuals, so two different data points. And if they satisfies these three conditions, then the decision is fair. Basically, any two individuals, X and X dash, so they if they have different protected attributes, so their protected attributes are not the same, but their other attributes are same or very similar, and then they should receive the same treatment, or the class, if it is a classification software, they'll be classified to the same class. This concept also gives us another definition, which is called counterfactual fairness. Basically, we take a data point, we only mutate or change the protected attribute value, and we see if it is classified to the same class or not. So we'll come back to this again a little bit later. Other than that, we have taken the mitigation algorithms. So in literature, there are these three categories of mitigation algorithms: pre-processing, in-processing, and post-processing. As the name suggests, you can see pre-processing algorithms are basically you apply before training the model, you change the weights or different data points, and in post-processing, you actually, after you get the decision from the model, you change the labels, or you try to optimize the labels so that it gets fair. In-processing algorithms can entirely apply another set of algorithms for training. We have taken these 7 different mitigation algorithms from the literature. Yeah, I'll not go to the details, but as I said, those follow the same patterns of which stage it is being applied to. This is how we designed our experiment. So first we evaluated, and so yeah, using those things, we have actually conducted this experiment first. So basically, for each model, first we have evaluated the performance, and then we try to improve the fairness using the mitigation techniques. So before applying the mitigation techniques, we calculate the fairness and performance, and after we again calculate the fairness and performance. We do this experiment multiple times to make it consistent, and also before calculating the fairness, we do this fairness specific pre-processing or some unnecessary pre-processing to the data. So this is how the fairness values look like for these 40 models. And you can see there are 5 different data set, and each of these data set actually follow kind of similar patterns, but some models might be fairer than others in the same data set as well. And what does this means? Actually, these are different metrics, so different colors represent different metrics. And so if the values are more than 0, so this is basically biased toward the unprivileged group, and if it is negative, then biased towards privileged. And you can see in the same dataset category 1, this model is much more fair than the others. And why did it happen? We investigated, and we have seen that this model, like this is using a construct called standard scalar. Basically, it's standardizing the data before training the support vector classifier, and which is causing it to be fair. We have also found instances where developers try to optimize model towards performance, which directly affect fairness. So here you can see GC1 and GC6, both are actually random forest models, and they are actually optimized through similar grid search. But they are so much different in their fairness. So these gray bars are the fairness. You can see GC1 is much fairer than GC6. And we identified the reason of these 2 models constructs, and GC1 is optimized for recall, whereas GC6 uses precision. And as a result, GC1 has like more false positives than false negatives, and that is why it is being more fair with respect to many metrics. So this actually suggests that developers, when they are optimizing, they are only optimizing for accuracy, and they should optimize carefully so that for a specific optimization construct, it does not affect the fairness. Here is another example which shows the fairness specification is necessary to give control over fairness. Yeah, take these 2 models, AC1 and AC2. So they are on the same data set, but they show very different fairness. And basically, AC1 is fair because it has used this construct class, so it equals balanced, which is making it fair. But so this one is actually controls the fairness directly, but the libraries do not document that, or the developers are not aware much about the fairness in this case. So these constructs also are related to the accuracy. So yeah, the fairness consideration is not there through the library constructs. As we mentioned, we have applied the 7 different mitigation algorithms on 40 models. For each of the models, we picked the best mitigation technique and plotted in here. And you can see for most of the models, at least one of the mitigation algorithms has been very successful, and we also found a few patterns in their mitigation techniques, which I'm going to talk next. So we have found that models in the same dataset often follow the same mitigation pattern. When I say mitigation pattern, I mean like, so in the same data set, the same mitigation algorithm is performing good to make it fairer. For the other data set, we also see similar patterns. So this indicates that specific mitigation techniques actually work on certain type of data set. So yeah, I'll try to summarize. The most important finding here is there is a large gap between fairness research and practice, and we need more library support and specification to control model constructs. Also, until now, it is not very clear that what is a good fairness threshold and which metric to use for a given task. So this is a problem of requirement analysis, and further research would be necessary in that direction. Our evaluation also suggests that by leveraging the existing techniques, it is possible to build automated tools to localize fairness issues. Like there are some APIs which are directly causing the fairness bugs. And finally, choosing mitigation algorithms and resolving the trade-off. So this is an optimization problem which need to be solved in the future. So yeah, I'll just wait here. If anybody has any questions, then I can take that.
So I have a general question. So does the problem domain of these data sets make a difference somehow in what you would expect? So I'm thinking, let's say for insurance rates, statistically speaking, men are more prone to dangerous driving, and so insurance companies intentionally set a higher premium given all the factors the same for men against women because of just the risk factors involved. So are things like that, I guess the bigger question is this fair or not fair, but are things like that also taken into account in these problem domains? Because like you only showed a sample of your data sets and it does vary quite a bit by domain, right?
Yeah, actually it's a very interesting point. So yeah, I didn't talk much about my data sets, but there are like credit approval and loan approval, as well as like crime prediction. But the one you just said is a little bit different. Here the software can intentionally try to penalize the men or women. So we have seen the similar situation in some medical applications. For example, in prostate cancer detection, it will not be similar for men and women inherently, and that is not. I mean, if more men are classified in a certain groups, that is like the pattern already present in the data. So in those cases, that will not be considered as a fairness concern, but this is not. This is more of a ethical problem construction thing. I mean, if somebody says that yes, even if men drives less safe, their insurance have to be the same. If the government says that, then that has to be considered as well. So first we need some requirements, or we need to set the bar of fairness, and then we algorithmically define it into our metrics, and then we calculate it. So I mean, until now in the data sets I have considered, the fairness are well defined based on the protected attributes and the favorable decisions. But in the one you described, the favorable decision is not clearly defined. So if that make any sense.
Okay, I have a follow-up, but I see there's another hand up and we can wait till the end.
So maybe just before we go to the next question from Joy, Sumon, do you have more slides that you'll be covering, or?
Yeah.
Okay,
yeah,
so maybe just for the sake of time, we'll let you continue, and then we'll take the questions at the end.
Okay.
So maybe, yeah,
that makes sense.
That would be better if
Yep.
yeah.
Thanks.
Joy, Sohaib, we'll take your questions at the end. Okay. Please
Okay.
go ahead.
So yeah, I'm going to talk about my next work. So let's go into this. So what are the challenges in identifying fairness in machine learning software? Firstly, in machine learning, we learn from the data. So if the data itself is biased, our software would be unfair as well. And secondly, machine learning is currently more of a black box, and it actually calculates some complex structure which is hard to reason. And many of the prior work actually proposed fairness metrics that so the ones I just showed actually measures fairness holistically at the end of the decision made, but we cannot say that this component is fair or unfair. So in this work, I tried to calculate the fairness of a specific component in the machine learning pipeline. This is what a machine learning pipeline, canonical pipeline looks like. The training data goes through a set of pre-processing stages, and before feeding into the machine learning classifier, it's fed into and this is the classifier, and then the trained model is operates on the test data to make prediction. So what are these stages? It can be missing value removal, or data encoding, or maybe normalizing. Sometimes a subset of features or examples are selected by sampling. Finally, a model is built by the classifier such that decision tree or support vectors and so on. Here, previously, fairness has always been evaluated in the end for the ultimate prediction. We don't know fairness of these data transformers. So we collected data transformers, which are well-known algorithms like PCA, SMORT from those libraries, as well as we collected some custom pre-processing like feature creation or missing value removal, etc., and tried to evaluate the fairness of those. So here is a simple example. The developer builds the machine learning pipeline using Compass data for predicting the future crime. So first, the developer performs custom data filtration, and then some imputation is done for missing values. You can see there, this is the imputation, and then another different imputation is done on a different feature F2, followed by some binarizing some variables. And finally, a logistic regression classifier is trained using the preprocessed data. So the existing metrics show that the final outcome is biased towards Caucasian defendants, but what is the fairness of these preprocessing stages that I just showed? Therefore, in this paper, we proposed a method to evaluate fairness of the stage SK. Specifically, a stage SK operates on the data already processed by the previous stages, so S1, S2. We used causal reasoning to identify the prediction discrepancy made by a specific stage. Next, I'm going to talk about this. So identifying causal effects has been an integral part of scientific inquiry for a long time. It helped to answer a wide range of questions like understanding behavior in online systems, or effect of social policies, or risk factors in disease, and so on. For example, in software engineering, causal testing is widely used. Given a failing test, we experiment with a set of test passing inputs that are close to the failing test, and in order to find what is causing actually the program to fail. In this paper, we also use the causal model proposed by Pearl, and we intervene on one variable of interest at a time and then observe the change of the outcome. So causality and fairness has been also studied in the literature, to find whether the age of the people is affecting the career approval or not by mutating the actual age. And Kalhotra et al., so they used the method to propose fairness testing, and they mutated the protected attribute by keeping other features the same, but only mutating the protected attribute. And then they see that does it change the prediction or not. So if it changes, then it's fair, otherwise it's unfair. And what we did is we made intervention on the system and not on the inputs to observe the causal effect of the pre-processing stage in the pipeline. So basically, we intervened on some stage SK. And our formulation looks like this. We create an alternative pipeline P star from a given pipeline P by removing the pre-processing stage that is in consideration. Well, in some cases, a stage cannot be removed. In that case, we replace it with some base stage. And if we have these predictions made by the pipeline P and P star, which is the Y cap, and then we look at the discrepancy between the Y cap and Y cap P star, then we get this impact set I, which basically tells that the impact of the pre-processing stage. And then we define this stage specific fairness criteria which is measure the fairness based on the impact set. And here the aim is a metric which we took from the previous studies. So in our causality, we have actually calculated the impact of a preprocessing stage and then used previous metrics to compute the fairness of that impact. So this is some the 4 novel metrics that we proposed based on. So these different metrics are basically based on different fairness criteria that we have shown previously. So this is based on the metric SPD. You can see we have calculated the impact, like compute the impact for each of the so if like the impact is towards favorable, then we calculate that. If it is not toward favorable, then we also track those. And if there is no impact, we so these are 3 different categories, and then we calculate these or summarize these for both unprivileged and privileged, and then we based on that metric we propose this new metric, which is basically stage specific fairness based on the metric SPD. And similarly we do that SF EOD, SF AOD, and SF ERR, and those are different metrics that I described previously. All right, so we conducted a thorough evaluation of on a benchmark of 37 pipelines. We have taken some of the benchmark models which are appropriate from our previous study, as well as we incorporated from 2 different other studies. And for each of the pipelines, we have found these many stages, and these are different preprocessing stages. And then our experiments were designed to first capture the causality in the stage, and then calculate the impact based on those metrics, and finally compute those metrics. And while doing that, we have to have like follow the ML best practices like data isolation and some random test split and so on. Okay, so we answered these mainly 3 research questions. First, we evaluated the fairness of different preprocessing techniques, and then we tried to find the patterns of different data transformers in the libraries. So we cannot do that on the benchmark because then the comparison is not uniform. So we created vanilla pipelines from the benchmark ones, and then applied different data transformers from the library on each of the situations. Finally, we tried to show the fairness composition. Basically, we call the fairness of the stages the local fairness, and the fairness with the holistic fairness is the global fairness. And how and answer that question, like do that local fairness is composed into the global fairness. Okay, so here are a few key findings from our evaluation. We found that in real data sets often contain missing values. The pipelines use different imputation techniques like replacing with most frequent. Essentially, some people get assigned. So yeah, I mean, pipelines ignore some whole data instance that contain a missing value. That also change the data distribution. Although this method might help the accuracy, we found those worsen the fairness. The size of bars represent the amount of unfairness here, and positive values denote the bias toward unprivileged, and negative values towards privileged. So another finding was like when creating new features, so the feature generation techniques are unfair in many cases. Like in one pipeline, they were trying to convert the education into qualification. Like if it is preschool, then call it dropout, and 10th grade, then call it high grade, and so on. So in these cases, that adds some biases in the data, which actually reflects in the prediction as well. Other than that, these are data transformers, which are actually built in data preprocessing algorithms present in the library. So we applied those in different situations on all of the data sets to find out similar patterns. And we found that, for example, among all the transformers applying sampling techniques like SMOT or some undersampling techniques like all KNN actually always introduce bias. Okay, so yeah, especially in RQ3, we showed that local fairness, which is basically fairness of stage, contributes to the global fairness. And to illustrate this further, suppose this is the pipeline, and these two red stages are biased towards group A, such as a male, that is making the whole pipeline unfair. Now, what if we replace this one with another biased stage that is biased towards group B, such as female? Our case study shows that we can, based on our stage specific evaluation, we can instrument the pipeline to mitigate this bias. Yeah, I'll try to go a little quicker here to talk about some other work. So this work was not directly related to fairness, but while working with these data science pipelines, I also done some literature survey as well as some empirical evaluation to show the the design and architecture of data science pipelines. So in this work, so basically design and architecture of traditional software has a long history of research. And in traditional softwares, we have these stages like design or implementation or maintenance. But in data-driven software, they are significantly different because of their data-driven nature, their uncertainty in their prediction, or because of its problem with the interpretability and so on. That's why in many research, they use this construct called data science pipeline, which we studied extensively and uh, uh, tried to show a representative structure as a software construct. This is how a simple data science pipeline would look like. They have different stages. So basically the collection of stages from acquisition to cleaning or curation and then modeling and so on are called data science pipelines. And in this paper, we have answered like what are the typical stages and how they are connected, or do the pipelines differ in the theory and that in the practice. We actually looked at a representative pipeline, as I said, what are the typical stages, and also provide the proper semantics and vocabulary of the stages, and then looked at the organization of the stages and whether the feedback loops are present or not, and so on. And then what are the different types of pipelines available. So this is how, to answer those questions, this is how our study design looked like. We took 71 pipelines from literature. So basically there are different pipelines in their specific situation. People proposed those pipelines. So we have done a literature review, and to study the pipeline in the small, we actually collected 105 pipelines from Kaggle, and we parsed those notebooks into AST, and then parsed the APIs and mapped each APIs to a stage to automatically generate the pipeline. And finally, we started pipelining the large. So there is basically pipelines found in like large data science projects in GitHub. And we found different representations, like different patterns in their stages. So in the theory, you can see there are 3 different layers, and so these are representative. As I say, like we actually manually followed the open coding scheme to label each of those 71 pipelines, and then collected the vocabulary and what those stages actually represent. And then we found that different stages like post-processing stages are not found in the small, and in the large we have found several different different patterns. Like the large projects actually in development phase, the developers follow this pattern on the top, like they follow the modeling, training, and evaluation, and create the pipeline. But in the post-development phase, people can retrain it, or they can use the model as it is, or maybe modify the model itself and training it for evaluation multiple times. So I'll not go further details, but you can look at some other key findings which might instigate research in this area. So finally, I'll talk a little bit about the work that is under submission right now, which is fairness verification of deep neural networks. I'll try to finish within 5 minutes. So here, this is the definition of individual fairness that I described previously. In individual fairness, any two individuals, if they are similar but not similar in their product attribute, they should have similar classification. And in deep neural networks, if we want to verify it, our goal is to provide formal guarantee that this network satisfies the conditions provided. And some work has been already done in this direction, like Albarguthi et al. And Bastani et al. So they actually proposed probabilistic verification, but that one was for group fairness. And as I said, like group fairness always calculates the probability, and that's why the probabilistic verification was appropriate there. And John et al. Actually proposed individual verification fairness, but for ML classifiers like logistic regression or kernelized models. And fairness testing literature actually showed that the success of the definition of individual fairness in fairness testing. So that one was important because developers can directly look at the fairness problem and they can fix it. That's why we are interested to start verify individual fairness for DNNs. This is a simple DNN look like. There are these input layer and output layer. There are hidden layers, and each layer, these are neurons, and the neurons has basically two different computation parts. One is the weighted sum, which is actually computed from the weights and the values of the inputs. So this is how the weighted sum is calculated, and then after that, the linear, the piecewise linear operation, which is basically ReLU. In this work, we looked at the ReLU-based networks. So, and this is how each of these nodes are computed, and finally, we take based on these outputs, we classify. We have a classification network, and yeah, so verifying a property in DNN is challenging because of this piecewise linear part, because you can see if the value is less than 0, it is transferred to 0, and that's why we cannot directly compute like whether there will be the nodes will be always activated or always inactivated. For n neurons, there will be 2 to the power n branches, and that's why the verification becomes interactable very quickly. And in our so this is basically our problem statement. We have our post condition transferred to the neurons, as well as we have our precondition transferred here, and this is how we transfer the fairness conditions into the neuron level neural network. And then this is our fairness verification query. It has these 4 parts. One is the domain constraint, basically each of the input neuron here, and this has its domain constraint, like it has a range, and there are fairness precondition, which is basically the individual fairness definition that I described, and the outputs will be similar, and that will satisfy the fairness post condition. The fairness post condition we got from basically what kind of neural network we are using. If we are using sigmoid at the end of the layer, then this is our transfer post condition. This is the overview of our approach. What we did is we divide the inputs into multiple regions. Yeah, so basically our approach takes these two things. One is the trained network, which we want to verify, and another one is the verification query that I just described. And first we divide the inputs into multiple regions and assign each DNN copies to each of these inputs. So for each input, our key idea is we notice that for each input we have many of the neurons remain always inactive, and that's why we can prune this network. And when we prune this network for a smaller partition, then the verification tasks become tractable. And here we use two different pruning technique. One is the sound pruning, and another is heuristic based pruning. Sound pruning is basically based on the interval arithmetic and singular verification, and heuristic based pruning is we profile the neurons and do the weight analysis to see if this will be always active or always inactive. So this is the input partitioning. We equally partition the inputs. For each of the features, we take a smaller part of the feature, and when we do this, we have a very smaller constraint for each of the input neurons as well, and that's why the next part becomes easier. So if I go to the next part quickly here, if we have a lower bound and upper bound, a shorter a constraint, lower bound and upper bound here, then the next neurons we actually calculate based on the interval arithmetic what will be the upper bound and lower bound of the hidden layers. And that's why in many cases this is always negative, and that gives us this, there is no effect on the prediction of this neuron. Basically this neuron will not affect the classification of any individual who will be in this input region. And apart from that, we also do the singular verification, which actually tells that if the precondition is this lower bound and upper bound, and this is the post condition, this will be always 0. And then we use a SMT solver to solve those verification queries if this is always inactive. So yeah, we are answering the same question until now, if this neuron, each of these neuron is always inactive. And we do this layer wise to identify those networks. Finally, I have said that there is a sound pruning, and this is the heuristic pruning. The previous two stages are sound, but in this case, we try to see which neurons are almost always inactive. And that's why we profile the neurons. We run a simulation with multiple, with like thousands of inputs, and try to see which are how many times these are activated. And we used a statistical technique to identify the neurons which are always inactive. So our results show that.
Sumon, I'm sorry to interrupt you, but if we can wrap it up in a minute, because I want to leave some time for questions. I think there will be some questions for you. So if,
okay,
it would be great. Thank you.
Okay, thank you. Yeah, so yeah, I'll wrap it up. SMT solvers cannot verify in very quick time, but using our approach, we have shown that we can verify many of the partitions very quickly. And the heuristic based approach pruning is only applied when the sound pruning is not successful. And we have also shown that the additional time taken is very low. And we have a few future directions, like we want to do some fairness monitoring in training, when there is a training of a boosting network based on the previous boosting round, the next boosting round is modified, and we want to modify the regularizer to make it fairness aware. In another one, fairness monitoring in production can also be proposed, like until a certain point of prediction, we want to say that if our the software is uh, satisfying that condition in the production. So other than that, the fairness composition has not been studied extensively. There are many multiple situations, like in hiring decisions, there are multiple stages where some people are selected in the first interview, and then they are selected in the second interview, and some initial result has been shown to show that if all the stages are separately fair, but then ultimate selection is not fair at the end. So I'm ending it now. I'll thank my advisor and also other lab members in my laboratory for software designing. So I'll stop here, and I'll take any questions you have. Thank you for listening.
Thank you, Sumon. We can open it up for questions. We have approximately 5 minutes. I know, Sohaib, you had your hand up. If you want to go ahead, you can unmute and ask your question.
Thank you for the nice and interesting topic and presentation. My question is very simple. So we speak here about the fairness, and it's kind of variety of accuracy. So it's related to the accuracy. So when the model is not accurate, but it's not accurate against a specific type of class in the training or in the population. So how you can elaborate on what the exact difference between when we speak about just fairness in general or just accuracy?
Yeah, so we cannot actually talk about one thing separately. As you were just saying, they are very related, right? But what we have seen is when developers are writing code, they are mostly considering the accuracy. And when we are saying accuracy, it's for all the classes or all the groups. But when we are looking at different groups separately, then there are disparity between that. So we cannot look at one property separately here when you're considering accuracy or fairness, but you have to look at the trade-off.
Thank you, Sumon. Maybe I'll take my power as a chair and ask. Ajoy is here. Okay, Ajoy, please go ahead.
Hi, thank you for your wonderful presentation. So I want to ask, like, for your empirical study for the for the first paper, you used Kaggle, but Kaggle is a competition site. So the model you will find are based on competition that are actually going on. Like, for example, one may be related to improving accuracy, one may be related to improving fairness. So how did you tackle that? Like, they might be biased on based on the competition you are collecting the data from.
Right. So as I said, like they are not considering fairness at all. And since they are competitions, there is a target for the score, and in most cases they are the accuracy, and they are optimizing for accuracy. But the reason for taking those models is basically we're trying to see what is the fairness situation in the wild, and how much unfairness exists, and what is causing those unfairness. So so they are not fairness aware for sure, but we are trying to see what is causing them to make them unfair.
Thank you, Sumon. Diego.
Hi, Sumon. Thank you very much for the presentation. My question is about tooling and how they have or have not yet given support to fairness. So let's say scikit-learn. We do grid search to find the best parameters, but always focusing on accuracy, AUC, and all of those metrics. Is there any support for like doing the sort of Pareto multi-objective optimization that focuses on accuracy and fairness at the same time, or this is not something you see in the libraries today?
Actually, there have been some algorithms proposed in the literature which do that, but as you are saying, the most used ML libraries are still not using fairness as a first-class citizen, and there are some constructs that we found are directly affecting the fairness, but they are not well documented. I mean, not documented for fairness. So you have to, if you have to do fairness and accuracy together, you have to use some algorithms from literature, and you have to write your algorithms. And there are some tools available as well, like IBM developed the AIF 360, and there are some other tools like Aquitas or Themis. So those tools are aimed for that task, but in general, for the ML developers, fairness is still not there are not much tools or things to use.
Okay, thank you so much.
Thank you, Sumon. Khalid.
So thank you so much for the presentation. I wanted to ask about your experience with using either the metrics or the tools for fairness, and how well do they perform when you have multiple classes in your data set that you want to check for privilege or not. So when you have like sex and age and multiple other privileged and non-privileged classes, how well do the tools perform, whether it is measuring or like trying to optimize for fairness? Do you find that they are less performant when there's multiple classes?
So if you are only considering about calculating or computing fairness for multiple classes, that should not be a problem, because you can the fairness metrics are designed in a way that you can take any of the group, and the other groups could be like, you can say that Caucasian and non-Caucasian. So all other races can be in the group of non-Caucasian, and you can calculate that. So when computing, that should not be a problem. But when you are saying like when optimizing for fairness, then it is a problem, because you don't know how much data you had in your training data for Caucasian or African American or other people, right? So I mean, if your training data if certain groups are very much underrepresented, optimizing for that or being fair for them is most challenging.
Perfect. Thank you so much. Thank you.
Yep.
Thank you, Sumon. Maybe we'll stop with the questions. Just one final question for me, Sumon. So has there been any comparison on the fairness metrics? Or how unfair are fairness metrics?
Yeah. I mean, this is, I mean, the actual answer is I don't know. I mean, if one metric is better than other, because it depends basically on the requirement. So some company can say this is my requirement, and this has been a long debate on that. Like in the crime prediction, as I was saying, like in crime prediction software that has been used in many United States. In Florida, they have used one metric, and in other. So when one company was blaming that, they are saying this is unfair with respect to that. And when they're defending that, then they're saying, no, it's fair to that. So, but again, it is also mathematically provable that there is an impossible theorem in fairness. Like you cannot satisfy all the metrics at the same time mathematically. So it's an optimization problem, and also a problem of in which context, which requirement you are gonna solve.
Okay, thank you very much, Sumon. Once again, I guess we would clap for you if this was not virtual, but thank you for the talk, and thanks everyone for attending and for everyone who asked questions. And à prochaine, until the next talk that we will have with the SE for AI. So thank you.
Okay, thank you everyone, and also listening to me and inviting me in this talk. Yeah, see you soon. Thanks.
Bye, bro.
Thank you, Sumon. Thanks, everybody.